When we solve rational equations are just equations that have rational expressions in them, which essentially just means that they're equations that have fractions in them, which we've already solved once before. We solved, whoa, that's not what I want. There we go. We solve things like this, like 2/3 x minus 8 equals like 1/5. I don't want to do 1/5. I'll do 1/2. I don't want to multiply 8 by 15. So how do we approach this? If you think back to like the first week of class, it was a while ago, but what's the first thing we did with these guys?
Clear fractions.
Yeah, we cleared the fractions, right? So we multiplied both sides by the LCM of the denominators over 1, because that allowed us to cancel all our denominators. So we did 6 times 2/3 x minus 6 times 8 equals 6 times 1/2. And we can do these calculations in our calculator, but just in anticipation of these being variable expressions instead of numbers, let's look at how these actually cancel the denominators. So we can rewrite 6 as 2 times 3 over 1. Six times 8 is 48. We don't really have anything interesting to do with that one because there is no denominator, right? We're just multiplying two numbers. And then we can write 6 as 2 times 3 over 1. And then we see that the 3 cancels here and the 2 cancels here. And then like the only denominators we have are 1s, which we can just get rid of because dividing by 1 doesn't change the numerator. So we end up with 2 times 2x minus 48 equals, what, 3 times 1? So that gives us 4x minus 48 equals 3. And this is going to turn out really nasty because I just made up numbers, but 51. So x equals 51 over 4. Yeah? Did I rush that and mess it up? No, I think that's true. Yeah? Okay, so this is the same general process we're going to use if we have rational expressions rather than just numerical fractions in our equation. So if we have fractions that contain variables. So there's only one thing we have to worry about. So remember that when we find the domain of a rational function, so when there's a fraction, that we have those restricted values, right? We can never plug 0 in for a denominator, or we can never plug in a number that makes the denominator 0. So if we had like an equation like, let's see, 3 over x plus 5 equals 3 over x. Do you guys agree that, so I'll just tell you, this has no solution. If you look at it, I think you'll come to the same conclusion if you just kind of like stare at it for a minute. Do you guys see that why it has no solution? So like if you were to subtract 3 over x from both sides, you'd get 5 on the left and 0 on the right, right? So you'd get like 5 equals 0. Which means which just isn't true, right? So we kind of know intuitively, just because it's a simple equation, just by looking at it, that there's no x value I can plug in that makes this true. But if we try to solve it the same way we solved up here, well, what's our LCM of our denominator? Yeah, it's just x. So the only denominator here is x, and so that's what our LCM is. So we would multiply by x over 1 times 3 over x, and then x times 5, and then x over 1. So the same exact process we did with numerical fractions. We just happen to have a variable in our LCM now. And so then these x's will cancel and these x's will cancel, and we end up with 3 plus 5x equals 3. And if we subtract 3 from both sides, we get 5x equals 0. And so x equals 0, which is a little bit troubling because we already concluded that there's no solution to this equation, and x equals 0 is a solution. And so where these things come up, this is what we call an extraneous solution. Which is, so when you solve an equation, you're essentially determining all of the possible solutions to the equation. But then if one of them doesn't happen to be in the domain of any piece of it, then it can't actually be a solution because you can't plug it in. So if we look up here, if we think about like the domain of f of x equals 3 over x, for instance, like we see that x can't be 0, right? Does everybody see why x can't be 0? So we call it, we call 0 a restricted value, is a restricted value. And so any equation that contains expressions that correspond to functions that have restrictions on their domain present the possibility of this extraneous solution situation where, like, I clear fractions, so when I solve this equation, I get a perfectly good solution to that equation, but it turns out that when I plug it back into the original equation, it doesn't actually work because it makes both sides undefined. And like undefined isn't like a number, so you can't be like, oh, the equation's true because undefined equals undefined, right? Like you have to have a numerical value on both sides in order for them to be equal. So in this case, we say that there is no solution to the equation. And that's because the only possible solution that we found is a value that I can't actually plug in for x, because it makes some or part of the equation undefined, so one or both sides. Does that make sense? And we'll formalize this a little bit as far as the process goes. But the idea of an extraneous solution hasn't come up yet because all of the equations we've solved have involved polynomials. So they've either been linear or they've been like x squared or something like that. And all polynomials have a domain of all real numbers. So whatever x value we get will work when we plug it back in. Whereas these fractions, remember that when we found domains, fractions always present some sort of a restriction on what x can be in the domain. And so that's where extraneous solutions come up. So when we solve like square root equations, we'll run into the same problem because there's a restriction on numbers that you can take the square root of. It's possible to get solutions that don't actually work in your original equation. It doesn't mean that you made a mistake solving the equation. It just means that you came up with this situation we call an extraneous solution where your possible answers don't actually make the equation true. So let's do another one, and we'll write out all the steps for solving these things because there's kind of a few of them. So solving rational equations. So let's do an example as we go through them. Let's solve 2x over x minus 3 minus 6 over x equals 18 over x squared minus 3x. So we know, so as soon as I see that there's fractions here, the first thing I think of is I want to clear them. And I can do that because this is an equation, which is why it's different than like what we did on Friday when we were just adding and subtracting fractions, right? Those were expressions. We weren't solving for a variable. So when there's not an equal sign, you can't clear fractions because you don't have two sides to multiply by the same thing on. So because this is an equation and because it contains fractions, my first thought is to clear fractions, which means I need to find the LCM of the denominators. What's the first step to finding the LCM of a bunch of polynomials? We did this at the very beginning of class on Friday. Remember, we had like a list of polynomials and we found what the LCM was. What's the first thing we did?
Don't you just write down like what's in the first denominator and then look at the next one, and if you already have that, then you don't need it, and then you keep going.
Right. So yeah, we need our LCM to contain all the factors of all the denominators. Before we can go through that process, we have to get individual factors for all of them, right? So we have to factor all our denominators first, because that's how we see if they share any factors. So the first thing we're going to do is factor the denominators, and it's only the denominators. So unlike when we multiply and divide and we factor everything in sight, when we're solving equations, we just worry about the denominator because our first order of business is to get rid of the denominators. So we don't worry about anything that's going on top while we're doing that. So when we after we factor the denominators, then like Jaylee said, we can find the LCM by just building a product that contains all of our denominators or the factors from all of our denominators. So find the LCM. I didn't leave myself enough room to do it up there, so I'm just going to do it here. So my LCM, well, first I need to factor. So I have 2x over x minus 3. Well, x minus 3 is a linear factor, and it doesn't contain any GCF, so there's nothing to do to factor that one. And then minus 6 over x. And x is just a monomial factor. There's no addition or subtraction there, so there's no way to break it down. And then equals 18 over, well, x squared minus 3x has a GCF of x, so we can write it as x times x minus 3. So if I look at my first denominator, I see that my LCM needs a factor of x minus 3. And then if I look at my second denominator, does that bring any more factors into my LCM? Yep. So I need a factor of x, right? Because x isn't a factor of x minus 3, right? X minus 3 can't be written as x times something else. So those are two separate factors. And then if I look at my third denominator, do I need any additional factors in my LCM to take care of that? No, I have both x and I have x minus 3, so I'm all set. So my LCM is x times x minus 3. And then the next step is to find those restricted values that we talked about in the last problem. So sometimes it's like you can get to the end of the problem and then plug your solutions in to see if they work. But with these problems, I see more mistakes in people trying to plug their solutions back in than in actual solving it because they can get kind of hairy with all those fractions and stuff. So instead, what we do is we find these restricted values at the beginning the same way we find the domain of a rational function, and then we can compare at the end. So we're going to find restricted values. And we could look at each fraction individually and find the restricted values, just like I said, like we find the domain of a function. But instead of doing it 3 times, it actually works just to set your LCM not equal to 0, because your LCM contains all the factors from all the denominators. So if you have an x value that makes any one of the factors in your LCM equal to 0, it'll make one of your denominators 0. And so we're going to solve LCM is not equal to 0. So that is equivalent to us setting each of our denominators not equal to 0 and solving. You just do it in one step instead of 3 separate ones. So for my restricted values, we'll abbreviate those RV. I take my LCM and I say that cannot be 0. And so that means that x cannot be 0 and x minus 3 cannot be 0. And so x can't be 0 or 3. So just using that 0 product property, I had 0 on one side and a product on the other. So I just set each of my factors not equal to 0 and solve from there. So now we're ready to clear fractions. So we're going to multiply both sides. If I can write here, multiply both sides by the LCM. And remember, you're not trying to make the denominators the same. You're just multiplying by the LCM over 1. So every single term you're multiplying by exactly the same thing to clear fractions. So in this case, our LCM was x times x minus 3. So we've got, I'll try to fit it in here, x times x minus 3 over 1 times 2x over x minus 3 minus x times x minus 3 over 1 times our second term, so 6 over x equals x, oh, I forgot my x minus 3. X times x minus 3, there it is, over 1 times the right side of the equation. So 18 over x times x minus 3. And then just like we did with numerical fractions, we can now go through and just cancel any common factors. So we have an x minus 3 that cancels here, and an x that cancels here. And one thing to note is, remember that you can only cancel factors from 2 fractions that are being multiplied. So like, for instance, I couldn't like cancel those x minus 3s because there's subtraction between those 2 fractions. So you can only cancel like this when there's multiplication between the 2 fractions. So here we can cancel because those 2 are being multiplied and they have a common factor. Here we can cancel because those 2 fractions are being multiplied and have a common factor in the numerator and denominator. And then here we have both factors in common. And so from here, we basically just want to copy what's left over. So don't try to distribute or anything at this point, because that's usually how sign errors happen, is dropping parentheses too soon. So I just copy this exactly as it is, and then I can look at it and worry about how to get rid of my parentheses. So we have x times 2x minus, and I'll go ahead and write the 6 before the x minus 3 just because we're sort of more used to seeing 6 times x minus 3 than x minus 3 times 6, and then equals 18. And then to get rid of those parentheses, I need to distribute the -6. So we have 2x squared minus 6x plus 18 equals 18. And then our next job is to figure out how to solve this equation. So the question we want to ask ourselves is this linear or is it not linear? Is this a linear equation? You got a 50-50 shot.
No,
No, it's not. Why not?
because no matter what you do, it equals 0. And x can't equal 0.
So we can make any equation equal to 0, right? Just by subtracting everything that's on one side from both sides. But the reason this one's not linear is just that there's an exponent on one of our variables, right? So there's no way for us to combine both of these into a single term because one of them has a variable and the other one doesn't. So we can't isolate x, but you're right, we do want 0 on one side because that's how we solve linear or nonlinear equations. So the two types of equations we've solved so far are linear equations where we get everything containing x on one side and all the constants on the other. So we isolate the variable. And then nonlinear polynomial equations, we can't do that because we have multiple terms containing x. So we have to get 0 on one side and then a product on the other. So we're going to subtract 18 from both sides. And so now we have 0 on one side. We need to get a product on the other, so we need to factor. So we have a GCF of 2x. And then we'll set each factor equal to 0. So 2x equals 0. X minus 3 equals 0. So x equals 0, or x, whoops, just copying at this point. So x equals 3. I'm on autopilot for a second. So at this point, what we've found are all the possible solutions. So if there are any x values that are going to make this equation true, they are either 0 or 3. So 0 and 3 are the only possible x values that will make this equation true. However, oh, I didn't write this step. So solve the resulting equation. However, we already decided that x can't be 0 and x can't be 3. So although we did this correctly and we got two perfectly good possible solutions, we check back to our restricted values and we say, oh, those don't actually work, so we get rid of them. Which means that this equation has no solution. Because the only two possible solutions don't actually solve the equation. They don't actually make it true because they make one or both sides undefined. So that's the last step, is to compare possible solutions to restricted values and throw out extraneous solutions. So extraneous solutions are possible solutions that are restricted values. So if any of your possible solutions match your restricted values, we throw them out. So this is a bit of a long process. There's a few details that we have to keep in mind as we go through. So I think it's a good idea, like, as you're practicing tonight. So at first, to just keep this list like in front of you so you can like go through the process completely a few times, and then you'll just kind of internalize it. But there's just a few details with these restricted values and things like that that make it a little bit more in-depth than the equations we've solved so far. So let's do a few more examples. Oh, and I should mention, it's possible for, like, if you get two solutions, it is possible for both of them to work. It is possible for one of them to work. It's possible for none of them to work. So there's no, like, pattern as far as, like, all of them will be restricted values or none of them will be restricted values. I could get, like, 32 possible solutions and 2 of them have to be thrown out and the rest work or whatever. This just happened to turn out this way where both of them didn't work. So, oh wait, I should get that back here. Oops. Why aren't you working? There we go. Okay, so let's put this guy up in the corner so we keep in mind what we're doing, and we'll do another one. Say 2 over x plus 5 plus, no, I want that to be minus 1 over x minus 5 equals negative 16 over x squared minus 25. So first things first, we're going to factor those denominators. So x plus 5 is a linear factor with no GCF, and so we just put it in parentheses, can't be factored anymore. X minus 5, also a linear factor with no GCF, so it can't be factored anymore. Can x squared minus 25 be factored? Yeah, because it's the difference of squares, right? Remember, with binomials, if you have subtraction between your terms and both terms are perfect squares, those are the ones that factor. So this factors into x plus 5 times x minus 5. So then my LCM, I can write it really small up here. My LCM is what? Yeah, I need a factor of x plus 5 and a factor of x minus 5, and that'll contain all of those. So x plus 5 times x minus 5. And then for my restricted values, if I set my LCM not equal to 0, that means that x plus 5 is not equal to 0, and, whoop, forgot the 0, and x minus 5 is not equal to 0. So x is not equal to negative 5 or positive 5. And so now I'm ready to clear fractions. Let's see if I can fit all of this on here. So we have x plus 5 times x minus 5 over 1 times 2 over x plus 5 minus my LCM again over 1 times 1 over x minus 5 equals my LCM over 1 times negative 16 over x plus 5 times x minus 5. Just flip. Okay. So now we'll go through and just simplify. So x plus 5, x minus 5, x plus 5, x minus 5. I want you guys to solve from there. So we got 2 times x minus 5 minus x plus 5 equals negative 16. So things like that middle term are the reason that I always just copy what I have before I start dropping parentheses, because it's easy to miss that you have to distribute that negative if you try to do all the distributing and getting rid of parentheses like before writing it out. But you guys did a really good job actually of keeping those parentheses. So this distributes, and so this should give you this, and I think that's what I saw on everybody's paper as I was walking around. Yeah. And so x is equal to negative 1. Is that a good solution? Yeah, that's a valid solution because it isn't a restricted value, right? So the only thing x cannot be is 5 or negative 5. If we found that the only possible thing that x could be is negative 1, then that works. That's in that domain. So let's do a couple more just that maybe look a little bit different. It's just so you see them all, like the different ways we can word these. So let's see, how about this one's fun. So let's do negative x squared plus 9 over x squared plus 4 equals 0. Okay, so first thing is to factor the denominators. Can x squared plus 4 be factored? It can't, because remember binomials, so two-term polynomials can only be factored if they are the difference of squares. So difference means it has to be subtraction between the two terms. And the reason for that is that, like, if x squared plus 4 like could be factored into like something times something, so the only choice for the first term would be x, right? Because x times x is x squared. And then to get that 4, we would want to do like 2 and 2. But to get a positive 4, either both of those have to be positive or both of them have to be negative, right? And if they're both positive, then that middle term would add to 4x. And if they're both negative, it would add to negative 4x. So the only way to get a 0 in that middle term is for these to have opposite signs. But then we don't get our positive 4. So like in order to get that positive constant term, they have to have both the same sign. But in order to get the 0 in the middle, they have to have opposite signs. And since both of those can't happen at the same time, we can never factor if that constant term is positive. So our LCM is going to have to just be x squared plus 4. The whole thing. And that means to find restricted values, I need to solve x squared plus 4 is not equal to 0. Any ideas how I could solve this if I can't factor the left side? Because, I mean, normally we'd say this is not linear, right? And so we get 0 on one side and then we want a product on the other. But I can't factor the left side, so I can't get a product. Any ideas what else I could do?
Square root it.
So I can't take the square root here.
You gotta subtract 4.
So I could get x squared alone. So x squared equals negative 4. And this works here because there's no middle term, right? The reason that we have to factor, like with something like this, is that we can't combine 2x squared and negative 6x to get a single term that contains x. But if that middle term's not there, then we do have a single term that contains x that we can get alone on one side, right? So we can get a constant on one side and one term that contains the variable on the other. So then let's just think about this. What real number would you square to get negative 4? So we kind of have two possibilities, right? It's got to either be 2 or negative 2. Because nothing weird is going to happen where we can square negative 25 and all of a sudden get negative 4, right? But what's 2 squared? What's 2 squared? And what's negative 2 squared? Also 4. So are there any numbers you can square to get negative 4? Right? Because if you square a positive, you get a positive. If you square a negative, you get a positive. So there's nothing you can square to get a negative, which means that x squared just never is equal to negative 4, so we have no restricted values. There are no x values that will make the denominator 0. Another way you can think of it is like if you square a number, you always get something that's at least 0, right? Squaring a negative gives you a positive, squaring a positive gives you a positive, so x squared is never negative. So if x squared is at least 0, then adding 4 to it is at least 4. So there's no way to get back to 0, right? To get back down to 0 if you add 4 to a number that's already positive. So our denominator will never be 0, which means that any solution we get will work because there's nothing we can plug into that will make that fraction undefined. So now we'll clear fractions. X squared plus 4 times 0. So on the left side, we just get our numerator, so negative x squared plus 9. And then on the right side, what do we get?
0.
Yeah, anything times 0 is 0. So in those parentheses, I could have like a 25-term polynomial that has like degree 7,000. And multiplying it by 0 will still give me 0. So the upshot of this whole thing is one helpful property about fractions, which is that if you have a single fraction that's equal to 0, the numerator always has to be 0. So if you think about division in terms of like if I have 6 cookies and 3 friends, dividing 6 by 3 tells me how many cookies each of my friends gets. Well, if I have friends, but none of them get any cookies, then I must have no cookies to give, right? So that numerator must be 0 in order for each of my groups to have nothing in it. And so, like, there's nothing you can put in the denominator of a fraction that will make it 0 if the numerator isn't 0 to begin with. And so that's a property you can use all you want. I mean, you can always just clear fractions like we did here. But if you have a single fraction equal to 0, you can always conclude that the numerator is 0. It only works with a single fraction, though. If we had like 2 fractions added together is equal to 0, we can't conclude that those numerators are 0. So we get negative x squared plus 9 equals 0. We want to factor the left side. So this is one of the reasons that we always take that GCF out. If the first term is negative, we always pull out a negative. Because at first glance, this doesn't look like a difference, right? It looks like 2 terms added together. But if I take out my negative 1, then we see that we do, in fact, have the difference of squares, right? X squared minus 9 is a difference. Both are perfect squares. So we get negative 1 times x plus 3 times x minus 3 equals 0. So that means that -1 is equal to 0, x plus 3 is equal to 0, or x minus 3 is equal to 0. Well, this simply isn't true, right? So it's not going to contribute any solutions. This tells me that x is -3. This tells me that x is +3. And because we have no restricted values, like we don't even have to compare those to anything. Like any solutions will work because we don't have anything that'll make our denominator 0. So those are both good solutions. Let's see, we have 3 minutes. Okay, so there's just one other type of problem I wanted to show you. It's not really different, it's just a different way of presenting the same question. In fact, I think I can just bring it up from my last class if I can find that page. No, apparently I cannot find that page. It won't come back. Oh well, we'll just rewrite it. So it looks something like given that f of x equals x plus 6 over x, find all values of x for which f of x equals 5. So again, this looks different because it doesn't say solve and then give you an equation, but this is just a different way of giving you an equation to solve, right? We're told that f of x is equal to x plus 6 over x, and we are also told that f of x is equal to 5. And if both of those things are f of x, then they have to be equal to each other, right? So we would set our function x plus 6 over x equal to the output they gave us, which is 5. So both of those things in red boxes are equal to f of x, so they must be equal to each other. And so then what would my LCM be here? So my LCM is x. Do I have restricted values? Is there anything x can't be? So remember, x can't be anything that makes a denominator 0.
Can't be 0.
Yeah, x can't be 0 because x is my only denominator, right? So we know that denominator can't be 0. So then we'll multiply by x on both sides. And that gives us x squared plus 6 equals 5x. And it's time to go, but this, I'll do it really quick. X minus 2, x minus 3. At this point, there's not anything super interesting that's different from the last problems we've been doing. I just wanted you to see this different presentation of the same type of problem, right, where you have to set the two equal to each other, and 2 and 3 are not restricted values, so they both work. I wanted to give you the review for your test on Tuesday, so you can start working on that.